Hey, this is going to be the introductory video for the set of lessons called the Principles of Thermodynamics. Now, I want to tell you right now, this is not the kind of thermodynamics that you are going to see in a high school or college level chemistry or physics class. This is a college class designed to teach you more, go more in depth of what you already had some sort of foundation in on that you already saw in thermodynamics. So, I just want to tell you right now, I suggest that you've taken a chemistry course, physics course, and hopefully uh, calculus 1 and 2. Chemistry, just because I want you to already have some background in thermodynamics. Physics, because we will be working with work and energy, and you should have some idea of what that is. And then calculus 1 and especially calculus 2, because I'm going to present you a few formulas later on that knowing what an integral is or why I would take area under a curve would be rather important to understand. So I'm going to start off by defining for you thermodynamics. Now, technically, the definition of thermodynamics is the study of entropy and enthalpy. But since you don't have a good, firm understanding of what those are right now, I'm going to supplement this definition. It is the science of heat and work and all of the processes and properties related to heat and work. So that is thermodynamics in a nutshell. So I'm just going to begin talking about how we would look at things. So first, I would like to propose to you a 25 millimeter cubed block. And this block is made up of some monoatomic noble gas, in which particles have no, they don't impact each other. Just we're assuming a very ideal situation. So if they were to take up a 25 millimeter cube block, that would be 10 to the 20th atoms. That's a lot of atoms. That's just a hell of a lot of atoms. So they're flying all about. Now, we have two ways of looking at all of these atoms. We have the microscopic approach and the macroscopic approach. Now, what the microscopic approach does is we will be looking at every one of these atoms individually. Every single one of them, their height, their speed in all three directions. That's a lot. That's a lot to keep track of. That's three directions. That's three velocities. That's and that's for every single one of these atoms. And if you were to, that's a 6 right here. So that's 60 to the 20th different calculations we would have to do to define what the using the microscopic approach to define what this block is. And that is way too much for anyone to really ask of you. So we aren't going to be using the microscopic approach in this class. Instead, we're going to be focusing on the macro. Now what the macro is we're just saying, okay, this isn't 10 to the 20th atoms, this is just some amount of a gas. This equals a gas. And what the average kinetic energy of all these particles really is temperature. So instead of having three different velocities, we just have the temperature. And we also can find a pressure, which is just the average force the molecules of this gas are pushing against on this container. And we can also define other things. It's density, it's it's enthalpy, which you may not know what that is, and so on and so forth. We can define all of these different properties of this gas now that we don't see it as 10 to the 20th different atoms, but as a gas. And because of the laws of probability and just we can assume that the average is a good way of going about representing this block of gas instead of having to identify every single one of these atoms. It's much easier to keep track of, and we can actually use everyday instruments to measure and quantitate the properties of these gases. Now, I just said properties. A state is a collection of properties. Properties of a block, of just something that we're looking at. So a state is just this one collection of all these properties at a given moment in time or something like that. And properties, there are two types of properties. There are the intensive properties and the extensive properties. Extensive properties. Now, intensive properties are properties that are independent of mass. So that would be temperature, pressure, density. Now it's the letter rho, or even specific volume. Now what specific volume is just the inverse of density. Now that just means it's nothing special. It's more or less density. It's just flipped over. And the reason why we use specific volume instead of density in these problems is that we usually know the mass of what we're working with and we're looking for the volume. So using specific volume, which is the units for specific volume are meters cubed per kilogram, it'd be much easier just to multiply this by kilograms to get a volume, which is more useful to us than just having to do the inverse later. So a lot of thermodynamic tables that you'll be looking at later on will be using specific volume instead of density. And that more or less sums up intensive properties. And now we have extensive properties, which are the properties that are intensive properties. Those are ones that are dependent on mass. So that would be mass, because mass is very dependent on how much mass you have. Volume, not specific volume, just regular volume. And even energy. And I say energy because we will be working with energy. Heat is a form of energy, and so is work. They're both forms of energy, and the reason why it is an extensive property because, well, think about it. If you wanted to get a lot of energy out of something, like let's say your car, you wanted to go very far, you'd rather have 10 gallons of gas than 1 gallon of gas because you'll be able to get more energy, more work from the 10 gallons of gas instead of the 1 gallon of gas. So there is a lot. More mass means more energy. And I'm just going to wrap this video up with explaining a very basic concept of thermodynamics called the Zeroth Law of Thermodynamics. Now, you might wonder why it's a zeroth law. It's because people figured out, well, this is kind of a law of thermodynamics after they already defined the first three, and since it's so basic, so just there, they decided that it makes logical sense to put it before the first three laws. So that's why we call it the zeroth law instead of the first law. And it goes as follows. Let's say I had this body of mass A. It doesn't really matter what it is, it just is. And there is another mass called B. And we know that the temperature of A equals the temperature of B. So these two things are in some sort of thermal equilibrium. They don't have to be touching or whatever, but they have the same temperature. And let's also say there is some body C. And we know that the temperature of B equals the temperature of C. So there's another little connection between these two bodies. They have the same temperature. Well, we have T of A equaling the T of B, and the T of B equaling the T of C. Well, if you really think about it, we can just cut B out. That's just the middleman, and we can say the temperature of A equals the temperature of C. And this is the zeroth law of thermodynamics. If the temperature of B equals the temperature of A, then the temperature of C equals the temperature of B, well then the temperature of A must equal the temperature of C. It's a very, very basic concept that is the zeroth law of thermodynamics. Nothing more to it. That's it. And I hope you followed everything I did in this video. If there's anything you want me to go over again, please tell me. I am doing these videos to try and be helpful. So if there's anything that I'm making harder than needs to be, please tell me. And until next time, I'll see you around.